Mm-hmm.
Haley's baking this one. She wants to take anti.
All right, so welcome to calculus class. We're going to do the flip coin of calculus. So far we've been studying heads. Now we're going to do tails. And so it is called the antiderivative. So it's kind of like this. Whatever you just learned, just go backwards. Oh, and then you know what? For a little while, you're actually going to get confused. Like, oh, shoot, I took the derivative. I was supposed to take the antiderivative. And that's part of the learning process. We're good? So one thing is, we're just going to learn the formulas themselves today. We're good? And then next week, we're actually going to learn what they mean. And this is the funny thing about it. It's kind of like, what? Serious? And then we're going to put it together. So it's pretty cool. I love this section. I love sort of exploring this section here. So, but let's do practical stuff here first. You guys should know this here. If I give you a formula about position, what is the derivative? Slope, and you can do slope. I was going to say velocity. Is that okay? Velocity or slope? Okay, what's the derivative of velocity? Oh, we kind of mentioned it a few times in class here. Okay. Acceleration. Or in the math world, right, we call it concavity. Right? That's essentially what those are. Okay, so now the question is this. I can take the derivative from position, give you velocity, from velocity to acceleration. That's awesome. What happens if I started in velocity and I wanted to get back up to position? There it is. There's my antiderivative. I want to be able to go back up the ladder. And that's what essentially is first here. But before we do that, let's do definition, and then let's do some weird stuff that begins to happen because of this here. So definition. Let's go. We're going to call we just need to define a function here. We're going to say a certain function. We're going to call capital F for now. Is called the antiderivative of, hey, look at that. We're going to kind of combine two functions together of little f. So we're going to use capital F and little f to sort of distinguish between them. And of course, we're going to have to do it on a certain interval. On an interval, and we're going to call that interval I. That's cool. If this is true, if we take the derivative of big F and it gives us little f. All x in a certain interval called I. Okay, so proper definition, here it is, just so we have it. So let's look at some stuff here. Let's do the derivatives first. So I'm going to start our way backwards here. So exercise 1, let's go find the derivative here. Let's see, find. And of course, these are going to be very specific to get us somewhere here. Find the derivative. What would I like to do? Yeah, let's go with x squared. X squared, yeah, x squared. So x squared plus 10. So we've got to notice one little piece of antiderivatives. And everybody said? 2x. All right, that's easy enough. Okay, how about b? I'm going to go x squared plus 15. And here's our problem already. Same thing. So hold on. So then when I say, give me the antiderivative of 2x. Oops. So let's go one more just to sort of get it here. So C, just give me the give me the derivative of x squared. 2x. Okay. So here's our problem. Oh, hold on though. Let me do another one here. Wait a minute. I think we got into something here. How about if I do this? X squared plus X. So that's different. Why is it different, anybody? Tell me in English.
It actually shows the number that comes after 2x because there's an x.
Yeah, because there's an X, absolutely. Because you have a variable, right? The derivative of a variable is going to be something at least, right? But the derivative of a constant, that's going to be the 0. Okay, so let's let's graph these guys. I'm gonna, so exercise 2. This. These are fun notes here. Let's graph. Exercise 1. So we just need to make the graph connection here. So if I have x squared plus 10, everybody agreed? This is like this. X squared, we know x squared. So this is 5, 10, 15, 20. I'm going to go by 5s. Really what we have here is that for A. True, true, true. For B, when we went up to 15, let's see. So notice x squared is still x squared, is that right? It's this whole concept of this constant. And what's the connection to the graph?
Moves it up or down.
Moves it up or down, right? Because that's what constants do at the end of functions, right? So really we just have, see if this would make sense here. Let me do 1, 2. Yeah, let me, C would be just x squared, right? We know what x squared looks like, right? So here's what I got. So see if we can make this connection here. So I have my, by definition, I have my 2x here, right? This is my graph. This is my derivative graph, 2x. Hey, that's cool. I go like this. That's my derivative graph. My antiderivative could be one of many different possibilities. It's going to be this guy, but the possibilities are, it could be down here. It could be up here. Could be all the way down there, right? And it comes back up. So shucks, I have to account for that. I have to account for the fact that there's a range of antiderivatives, right, for one problem. All right, how should I account for them? I think I just said it maybe. The only thing that happens is this constant at the end, right? 10, 15, -5, -27, right? It's that little constant at the end. So let's do this. If I want to take an antiderivative, I'm going to add a constant to my antiderivatives. We good? So let's do this here. How about this? Let me give you theorem. I love to do it before we do theorems. I like to do it like this. So how do I account for all the different possibilities here? This guy at 15, this guy at 0, this guy's at -25. I'm going to do this. I'm going to say, you know what? The antiderivative, if this is my derivative, then my antiderivative is going to be x squared plus c. And if we use a capital C, we could have used an A. We could have used a G, whatever. Right? We just use capital C, and that means it's an arbitrary constant. It's some kind of constant. But we just accounted for all the different possibilities that could happen here. Okay, we good? That's one of those aha moments, like, yes, okay, I got you. Okay, now the theorem. All right, some more writing, guys here. If capital F is antiderivative of F on, that's funny, it's gonna be on and, so O-N, A-N, then, so let me write it here. It says then the most general antiderivative of F on I is, and there's a little, that's going to be, and we just did it anyways here. So it's just that. Where C is an arbitrary constant. Okay, just arbitrary constant. Sometimes we will define it, or eventually we will define it. I want to say sometimes because it just depends what the question is asking for. Sometimes the question will just say, hey, give me just the basic antiderivative. Later on in the course, we're going to actually figure out what that is. So let's do this here. Let's start off with we could do that. That'd be fun. Good, never done. Talk to me. What example are we on? 3. All right. Here's what we want to do. We want to find some antiderivatives of derivatives that we know. So some of these are going to be very specific. Some of these are going to be some rules that we'll try to do and make. So first one, let's jam with it. I think the trig functions are easier to start with. So I need this. If little f of x is equal to sine of x, give me capital F, bless you. Let the fun begin. Man, yeah, that's right. Because hold on, the derivative of sine is cosine, but that's not what I want. I want to go backwards. I want to go from sine back to whatever it does would actually give me sine.
Would it be negative cosine?
May says negative cosine x. Anybody agree, disagree? It's before 8 o'clock in the morning, so without coffee. So absolutely. So real quick here, let me give you some rules here. So we go like this. This is kind of like a quick little rule. So good there? It's SC negative S negative C. And it really just means this. The derivative of sine of x is cosine of x. The cosine x is negative sine of x. And then it starts repeating itself. So then you just keep on going down, or you just cycle back up, whatever you like. So derivatives go down. And antiderivatives go up. So again, just something that was needed. Sadie, do we ever talk about that? No. Oh. Okay. So if we went the next one, if the next level came down, it would be back up to sine, right? Sine of x.
Maybe we did that.
Okay, I remember mentioning it. It was kind of like this, just a quick little mention in class. So Amaya is right. Here it is. We got ourselves a negative cosine of x, and then Plus C, absolutely. We gotta have that constant because we're just doing a generic antiderivative. Okay, let's jam with it here. So we're gonna build these guys out. So cosine of X. I'm gonna look at the guys, just says, so antiderivative of cosine. Anybody? Sine of X, absolutely. Plus C, we're good? Yeah. It gets interesting, like a little boring now. What do you guys say? Or no, or it's okay. So I got sine and cosine. Let's see, I gotta do, oh, hold on. Let me actually do this. I'm gonna, sorry, Haley doesn't get the benefit of seeing it here. Okay, you can pass that for the sheets here, and you can take them to like. Haley, these are the formulas that are back of the book. It's the reference pages in back. And it's the ones that you want to go up to your derivatives. We're good? So AB, I got C. So we're going to, again, we're doing trig functions, right? And hey, that's right. Look at that number 13. That's sine to cosine. So that was B, is that right? So I don't know if you guys are on the same page with me. This is, it should be have a little 5 on the bottom of the page. Are you guys on page 5? Okay, so you guys, let's go back up here. So as far as numbers are concerned, which one is B? So this. And so remember, we took, that's the derivative formula reference sheet, right? So the derivative sine is cosine, right? So then the antiderivative of cosine is back to sine. That's what we're looking for. We're going to look for the sine to cosine and then cosine back to sine connection. That's number 13. Tell me if you guys agree there. That makes sense? Okay, you guys tell me what A is. Oh, it's not on the list, huh? We just kind of did it by that. Whoa, hold on. So this is crazy. Look at number 15. The derivative tangent, anybody? Secant squared. Derivative cosecant. Remember, we have all the trig functions here, right? Cosecant. Derivative cosecant is negative cosecant cotangent, right? Derivative secant, number 17, is secant times tangent. And the derivative of cotangent is negative secant squared x. Whoa, hold on. So let me do this here. What is the antiderivative of tangent? So we got sine, cosine. We did sine, cosine, and tangent, right? Yeah. All right, so again, the only thing we have is we have our reference sheet, right? We're just going backwards off our reference sheet, right? Okay, if you're confused, that's great, because it's still before 8 o'clock in the morning. So here it is, you guys ready for this? We don't know, I'll put a little caveat, yet. We're good? Because the only thing we're going off of is a little sheet. If I say this right here, give me the antiderivative of secant squared. It's tangent, yeah, so the antiderivative. Okay, so are we good? We are kind of stuck to this little sheet. And should we do it? Should I introduce you guys? Ooh, I gotta do it. I gotta do it. So you guys ready? Flip the page to 6. Here's all your formulas. Do we have 6?
Not on the sheet. In the book.
Did I not give you guys a form? Is it just
Oh, there
derivatives?
is no 6.
Oh, there's no, that's right. Okay, never mind. Okay. Okay. Sad, sad, sad. Okay.
Wait, see.
Yeah, she has it. All right.
Yay! My special gift. You can have that.
Wait, it's exactly, that's actually the same reference page.
It looks very similar. Yeah. It
This
looks
is just
very-
another edition of the same
Oh,
stuff.
gotcha. Okay. Okay, that's right. It's edition 9, right? Because that's why I chose it. We got something like that. 10 now? 8, okay.
Yeah, it's late.
Yeah, I chose, I figured out what Cal Poly was using, and I chose the same book. So
I can't really switch which edition were you, wait,
they're on 9, but it's still the Stewart book.
no,
Stewart is
but they're
kind
on 8 because I'm probably using 8.
of, okay,
I think they're not on the most updated book.
gotcha. Okay, but it's still the same book.
Yeah.
It's still the Stewart book. So.
It's exactly the same.
Mhm.
Not as updated. Cal Poly,
Okay.
There's,
So are we good there with we know certain ones, we don't know certain ones. We're just kind of stuck in doing some. Okay. So let's do this one here. So E, A, B, C, D, E. Yeah, it's E. Okay. Oh yeah, this would be fun. No, let's do this one first, just to get going. All yours. Anybody? Go.
X squared plus.
Awesome. Okay. F. Okay. If you think that was cool, then how about this? That should be, hold on, let me E this. Oh, I did F and then I did the function F. Ooh, toughy, toughy. Anybody got it? Oh man, what'd you get?
I got 1 plus C.
Let's see. Hold on, if you did that,
Oh,
you
wait,
took
it'd
the
be,
derivative of it.
Oh, I see now. I took the
Mhm. That's okay. And again, I would tell you right now, you guys are gonna do that in the homework. That's just the way I did it. And it's just like, oh shucks, I went the wrong way. Okay, so let's talk about this here. So notice we went from 2x up to x squared. So let's do what happens with the derivative on a power function? If I say, hey, look, take the derivative of x squared, what's happening here? What do we do? We take the 2, we bring it out to the front, right? And then what we do is we subtract 1 from the exponent. So let's think about this here. What I do is I divide by, I multiply. I multiply by my exponent and I subtract 1 from the exponent. Good? All right, let's do the exact opposite. Instead of subtracting from the exponent, we add. So in this case, it was a 1 here, right? So what happened is we took the 1, we added 1. There it is. I'm adding to the exponent. And instead of multiplying by the original exponent, I divide, but I'm dividing by the new exponent that I just had, right? Because with derivatives, what we do, we already have the original exponent. We just multiply by that. Sweet. Okay, so this case, it's the exact reverse. I add 1 to the exponent, and when I know what that exponent is, I'm going to divide by that exponent. So cool, let's see. So I'm going to add to the exponent. So 1, I'm going to add it to 2. Now I'm going to divide by 2 plus c. So we'll get a generic formula in just a second here. Okay, I'll go with this one here. How about x to the 4th power? Cool stuff, cool stuff. Okay, anybody got it? Ding, ding. We can go down the row. Like, I would love to pick on Zechariah first. Zechariah, answer is? Divided by 5. Thank you. Almost got it wrong.
There's
Okay.
some really funny memes where you forget to put plus C and like the world blows up. It's really funny. It's a serious problem.
Oh. Okay, I think we're ready for this one. I'm going to go with the generic one. Go x to the n. So any exponent. All right, I think we got it here. And what'd you guys get? X to the n plus 1. And then what do? Divide by the n plus 1 plus c. Perfecto. We're good? Sweet. You guys are learning awesome stuff. Did you guys know that you're going to learn this today morning when you guys woke up?
It's so much brighter.
I know. Oh, let's back up. Let's back up. Trivia question. When is the only time this will not work? There's one n value where it does not work. It's going to explode, blow up. The world will blow up. 0. Well, let's see. If x is equal to 0, right, then that just becomes 1, right? So then with 1, all we do is we actually just put, if that's, good job in doing that. If that's true, right, then this guy is going to be just back up to x plus c.
Oh, I see.
So notice, oh, hold on, this is so cool. Check this out. So really, if that is the case, it's still doing the same thing. Right, 1 plus 0, right, or 1. That is so cool, it's still the same. Okay, so 0 works. Yeah. Hold on. 0 is our problem, huh? So instead of starting at 0, what happens if I actually ended at 0? Would that be a problem? Yeah, that would be a problem. Hold on, if I have this right here, I had x to the negative 1, right? What do we do to do that? We would add 1, right? Negative 1 plus 1. And then we're going to divide by that addition factor. Is that a problem? Yes. Okay, so real quick here, the only time this guy does not work is when n is not, well, it works all the time, except for when it's equal to negative 1. So but do you guys remember? Yeah, I do remember. I still want to know when this happens. What is the antiderivative of x to the -1 or 1 over x? I'm pretty sure we had a derivative that gave us that. All right, gotta go digging. Gotta go dig into my sheet again. Anywhere on this page do I know going the other way? Anybody? ln number what on our list? 11. This is number 11, guys, on our list. Just take a look at that here. Yeah, the derivative of ln of x is equal to 1 over x. We've done that before. So then the antiderivative would be going the other way. ln of absolute of x plus c. Perfecto. Again, the only thing that can happen is now x being 0, right? Because you can't divide by 0. So we have to do a little qualifier here. So it says this right here, x. It works all the time. It works on the interval as long as x is bigger than 0 or x is less than 0. That's fine, but it just can't work with 0 itself. Okay, I think we got those. Oh yeah, hij. This is fun. All yours, guys, with this one here, hij. The antiderivative. Oh, I have to go. I forgot to go in order. Is that right? I already picked on you, Nicholas. Antiderivative of e to the x. I'll help you out. Pressure's on you. If you don't do it correctly, the world's going to blow up. Did you find the meme, Sadie?
I couldn't find the one I remember.
Okay, that's fine. That's fine. I don't have to look it up.
Yeah, I'll look it up on the computer.
I know. You can look at our little lists as well here.
Yeah, right. I was thinking because he says it's also just the same.
Absolutely, yeah. The derivative e to the x is still e to the x. So therefore, the antiderivative e to the x is going to be e to the x
Plus e.
plus c. Okay, world is saved.
No, terrible when you have to graph.
Well, you just kind of like. Graph. I do not like that chapter. I don't like graph. I like graph a little bit. I like
Okay.
this. I do like graphing. No, not Desmond. I love this.
Okay, let's take a look. Maybe not that one. Let me just change it up here. Oh yeah, so let's do this one here. Okay, let's just jam through the other ones here that we've done. We didn't touch, we didn't touch back on them. But remember we did hyperbolic functions, right? So then again, from our list, the antiderivative of negative sine of x is a hyperbolic function.
Negative.
Cosh, All right, so the negative and the negative stays.
So does, for the hyperbolic function, can you just do the same order that we did for like the sine, cosine, negative, sine, negative?
Absolutely. Sorry, man, I can't. Sorry. Notice that. So let's go with our order for sine goes to cosine, and then from cosine goes to negative sine, then negative cosine, and we go on, right? And real quick, let's do this together. So we got it here. So notice number 13 on your list, and then number 14 on your list. So notice the derivative of sine is cosine, And the derivative of cosine is negative sine. So it follows this little pattern right here. For the hyperbolic functions, notice if you drop down to number 25, the derivative of sine or sinh is cosh, right? But then the derivative of cosh is sin. So the order is correct, but there's only two. It just goes like this. The negative sign is not even in there. It just goes this way to this way to this way to this way. I mean, does that answer your question?
Yes.
Sweet. A, B, C, D, E, F, G. I'm just learning the alphabet. L. L is the next one. So I need to know, let's get into some heavy duty stuff here. I need to know this. And let me check something. As you guys are doing that, let me check something here. 3-9, I believe. Yeah. 9. Two. Huh, okay. What do you guys say? Answer is? Ding, ding. I mean, I think it's your turn.
Yeah, I got inverse and cosh.
And what,
X plus C.
yeah, and it's number 32, I believe, is that right? Sadie, can you check something for me?
Yeah.
On your list, not on that list, on the new book, can you check number 36 on your formula sheet?
Yeah.
Or I need to know the derivative of hyperbolic tan and then hyperbolic cotangent. I think there's a typo. Oh, no, hold on, that's just hyperbolic tangent. Okay.
One over
Yeah,
one
they're-
minus x, and then that's for tan,
Uh-huh.
and then cotangent is 1 minus, wait,
1 minus x
1
squared
over
again,
x
right?
squared, it's the same.
It's the same. Okay. I got to think about that
Wait,
for a little bit.
that shouldn't be the same, should it?
Ah, interesting. Okay. I'll let you puzzle that, Sadie, for a little bit. LM. Okay, and then this one, we're going to finish out with this one because we'll use it later on. I need that one. Use this one later on. Let's see. Back up to Zechariah. Zechariah, all yours. Answer is any one on the list there. Anyone that you can find. No, because that one has a square root. I'll just tell you, it's not a hyperbolic function. How about that? Not an inverse of a hyperbolic function. Second? We're on M, yeah. So 1 over 1 plus x squared. And it's not a hyperbolic function. Tangent inverse. Yes, awesome. Okay. Are we done? Was that good enough of exercise to start doing antiderivatives? Okay. Let's See if I can still do it the same way here. Let's see. Yeah, I could still do it the same way. Okay, you guys, LMNN. Okay, now let's get fun. That was just beginning stuff. All yours for this, 4 sine of x plus, oh yeah, of course I'm going to give it to you. Craziness. Of course, I'll work it out with you too. So I guess we could got to simplify this a bit here. So this is this, and let's do this here. Let's we can split this x into 2 different pieces. That's no problem. So this will be 2 to the 4. Is that good? Sounds about right. So this will be. Let me do it by piece here. So let's split first. And then this one's going to be 4 sine of x plus what? 2x to the 4th. I would agree there. Just subtracting, right? 5 and 1. That's good enough. How about this one? Square root of x and the x. Right, technically it's this right here over that right there, right? And we do a subtraction. You guys tell me, anybody? Yeah, we can, so there are kind of 2 different ways to do this here. Usually we can write it like this right here, right? Because that's a 1/2 on top and it's a 1. So 1 minus 1/2 is a negative 1/2. You can write it like that. You can also write it as that, or you can also write it as this right here. The preference is this one right here, because we're going to be doing the antiderivative. So I'm going to set that up so that I can add x to the exponent here. So it's going to be x to the negative 1/2. And I think we are ready for our antiderivative. Okay, so constants we don't need to worry about. Constants are just going to be there, right? So antiderivative of sine. But go back up to our little list here, right? Sine, cosine, negative cosine, and then it recycles again. Negative cosine, would you guys agree? Yeah, okay, so 4 negative cosine of x, dun, 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 and who am I picking on still? Was that guy picked on you last time, huh? Okay, Nicholas, all yours. 2 to the x to the 4th. Antiderivative of 2x to the 4th. Say again?
Trying to not go forward, it's like a regular rule.
Gotcha. So remember, this is a power rule, right? So that what we're going to do is we're going to add 1 to the 4.
Okay.
That's going to make a 5.
5 over.
And then we're going to divide by 5.
Yeah.
Yeah, absolutely. Ding, 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 done. Good there? Okay. And Amaya, all yours for this one. So x to the negative 1/2. It's not a negative 1, so we can use our little power rule, right?
X to the negative 3/2 over, or no, x to the positive 1/2.
Awesome. Yeah, negative 1/2 plus 1 would be a positive 1/2 over.
Over 1/2.
Over 1/2, yeah. And so in this case, what happens when we have fractions here, we're just going to take the reciprocal and multiply it by the reciprocal right away. So to clean it up a little bit here, I feel the world is breaking.
Let's,
Close one. So close. Okay. Fixing it up here. So capital F of X. How about a negative for cosine of X? Is it plus? I think it's plus, right? Plus. This one was just fine. This one was X to the 5th over 5. That was fine. And then it was, oh yeah, and this one's going to be now a minus 2x to the positive 1/2, and then square root of x, whatever you like at this point, plus c. Okay, we're good there. Okay, let me introduce you to a little bit of different notation. So what example are we on? Four, five?
oh, example, yeah, 4.
4. So just slight difference in notation here, guys. Can you guys find f if f prime of x? And of course, I'm gonna have to give you guys some fun stuff. Oh, yeah, it's this to the second power to the negative 1. And then, ooh, and I have something else, something extra special for you guys. And I don't like my and. Okay, there it is. And what? We have initial condition now. Notice it says that f of 0 is -2. So, oh, two things here. First is I want to find f, but notice what I know. I know the derivative, right? It doesn't have to be capital F all the time, right? That was just for a definition, right? So if I see a derivative and I want to find the original function, I'm using antiderivatives. That's one piece. Second piece is I do have some information. So when this all started off, when this function reaction, chemical reaction started off, the temperature was -2. That's what it was. So I think we could actually plug in the C value this time. Okay, with time remaining, let's jam. So I'm going to take this guy, the derivative. Ding, ding. And let's simplify this guy out. So e to the x is just e to the x, right? That's just easy enough. 20, I just want to keep as a multiplier. 20 is just going to be a multiplier, but let's really work with this here. 1 plus x to the second, and all that to the -1. What does that look like? It's the reciprocal, right? Reciprocal of 1 plus x squared. So tell me if you guys agree. That should be looks like it's a function inside a function, huh? It's one inside the other. All right, and I think we can get to this one, at least the generic one here. Let's see.
So why is f written as f to the -1?
Oh, awesome. Because I was all crazy. It should just be like that. So the little dash right there, that just means derivative. Accent mark, I guess, if we were in Spanish class. Okay, help me out here. Antiderivative e to the x. Okay, I'll help out myself. It's e to the x. And I need to know that one. Anybody in a sheet of paper? 20 is just a 20, right? 20 is a constant. We'll just multiply that later. But what is 1 over 1 plus x squared?
Inverse.
Tangent inverse of x. Bam. Oh, plus c. Is that right? Plus c. But that c we're going to figure out now because that guy is going to give us a value which will actually remember those different graphs that we did of x squared, right? We'll actually know the one graph that it works, right? So we have original connection. So if I plug in a 0, all yours. This is algebra now. Plug in a 0 for the x. The result is going to be -2. Find c. How about that? Let's go with it. And so I'm going to go with, let's see, the answer is -2. So -2 gets me e to the 0 plus 20 tangent inverse of 0 plus c. That's what I got right there. All right, anybody, e to the 0 power is 1, awesome. And then we've got to deal with the tangent inverse function. Oh, gee whiz, tangent inverse. Let's go back to trigonometry. And so inverse just means we're going to go back to our angle measurement, right? And so question is this, if tangent gives you 0, what's the angle measurement that it was before? Ooh, let's check it out. So 45, I think with 45, it was when tangent gave you 1, because these guys are both exactly the same.
Ooh, I see.
I'm just thinking maybe like this right here. So tangent of theta is equal to what? Y over x, is that right?
So that would be
180, you think? Could be. We're going to be in radian measurement as well, right? Because that's the way we think about it. I'm just thinking this here. If it's 0, right, that means y would have to be 0. Right? If y is 0, then what is x? Because there's only one time where 1. So I'm looking for 1, 0. And I'm looking for that angle measurement right there from the origin. Still 0, yeah, right? If it was cosine inverse of cosine, it would be pi over 2. It'd be all the way up here, right? But sine and sine inverse of 0 and tangent inverse of 0, they'll both be 0. So this is, I love it. There it is, just that plus 0, putting in all the little fixins here. That, subtract 1 from both sides. And I got myself, hey, I got myself a -3 for C. It's a little different than. And so final answer here is we just went backwards here. The original function after we found what after we knew what the derivative was, is that right there.